Recording, yes.
It started. Okay, thank you much. Alas, it started now. I'll say from the beginning again. Okay, so now what we learned from the previous class is that this is the only thing I wanted from you. The main thing is that how to write a reaction equation. This reaction equation will depend. For complete combustion, we do not want to see any fuel here. For theoretical amount of air, we do not see any amount of air in this side. So now I'm burning fuel, I'm burning with air. So when I say complete combustion, we do not want to see any fuel in the right hand side. And also we do not, because it is theoretical, then the air is just enough to burn the fuel. If it is not theoretical, then we'll see oxygen here. If it is not complete, we can see carbon monoxide or CH4 in the product. So this is, let us start here. All what I will be given is CH4. So the question will ask you, write the reaction equation for complete combustion with theoretical air for methane. So this is what here in this side. Then I add to that, I write here bracket O2 plus 3.76. So this is the first step I write in the equation. Then I add this part. Then I write here carbon will burn to CO2, so I add this. Then hydrogen will burn to H2O without writing any values here. So this will be CO2, H2O, and of course we add nitrogen here, and we write this bracket here. Then once we have done that, I start balancing the carbon. So carbon here, then I have to have one here. Start the hydrogen, hydrogen 4, and this is 2 here, so this has to be 4. So 2 by 2 is 4, so I have to add 2 here. Then I look for the oxygen. I have 1 mole here, O2, 1 O2, and another 1 O2 here. 2O means 1 O2. So 1 O2 plus 1 O2, this will give us 2 O2. Then I go for the nitrogen, multiply 2 by 3.76, so it will give us that. So this is number 1, you write that. Number 2, you add this bracket, it's always added like that. Number 3, you add CO2. Number 4, step 4 to write H2O. Step 5 to write Na2. Then balancing carbon, you see what you write here. So this is 1. Balancing the hydrogen, you get this value. Then balancing the oxygen, you get this value. Then get the amount of nitrogen. So these are the steps to have a theoretical amount of air for complete combustion of fuel. And we have here in this case the methane. Okay, so now let us go to, so this is what's mentioned here, how to get this equation here. Okay. Now what is the amount of air? This is the amount of air here. Is we will look at this when we come to the air to fuel ratio. So this is the air required to complete the combustion, which is this is the amount of air here. I have 2 moles of oxygen plus 2 moles of nitrogen multiplied by 3.76, and this will give us here for air I can say it's 1, so it's 1 mole of oxygen, 3.76 moles of nitrogen, so means that I have for the air it is 4.76. So it is 2 multiplied by 4.76. This will give me the number of moles of air required for theoretical combustion. Okay. As we mentioned here, we normal. So this is here is we got this per the amount of combustion here. So this is 9.52 moles of air divided by 1 mole of fuel. Remember here that when we write this equation, you have something in mind, that this equation is based on 1 kilomole of fuel. Then if we want to get the air to fuel ratio by mass, then we have this value, this is a mole, this is how many moles of air per mole of fuel. Then I multiply this by molecular weight of air, which is 28.97, divided by the molecular weight of fuel, which is 12 plus 4 will give me 16. So this will be the air to fuel ratio by mass. Okay, so this is, so far we have to learn 2 things. One is how to write the reaction equation. Second is how do you calculate the air to fuel ratio on a mole basis, and how to write the air to fuel ratio on a mass basis. We will still have more examples in that, and I make sure that at the end of this class, you definitely, every one of you are expert in calculating that. Okay. Now, as we mentioned here, that when we have actual reaction equations for the automobiles, for boilers, whatever, of course, we have to guarantee that we burn all the fuel. To guarantee that we burn all the fuel, then we add extra amount of air to make sure that you burn all the fuel. So now we say that 150% of theoretical air. This was the theoretical air. So when we write the equation, forget about this values here, 1.5 here. It is 1. If I write this for theoretical reaction, this should be 1. So CH4, as we have done this in the previous slide, we got this in the previous slide. Then we need here to be 150% theoretical air. It means that we will add more 50% more of the air. So we'll multiply here by 1.5, and then this will affect only oxygen here and nitrogen. So because we added 50% here, then we have oxygen here. How do we get this one? Is it 1 here? Because I have here, originally it was 1. I made it 0.5. So the extra amount now is 0.5 multiplied by 2. The extra oxygen now is 0.5 multiplied by 2, which give us 1 here. So now the equation was, this is 1. This is the theoretical air. If we write this 1, this is theoretical air. Now we make it 1.5. Means that we are adding extra 0.5. Therefore, in the products here, we have 0.5 multiplied by 2. This is the extra oxygen. So put 1 here. And then for the nitrogen, multiply this by 3.76 to give us the amount of nitrogen. So this is here is a reaction equation with 150% of the theoretical air, or we call it 50% of the theoretical air. For example, suppose your salary is 1,000 riyal. When I say we are going to give you 150% of that, so you are getting 1,500 Saudi riyal. When I say here what is the extra or what is the excess amount, then you say it is 500 Saudi riyal. So this is the difference between 150% theoretical air or 50% excess air. It is the same. Okay. So this is the amount of air per mole is 1.5. So now we can write here the air to fuel ratio. This will be the amount of air 1.5 multiplied by 2 multiplied by the number of moles of air. So this will give me the air number of moles per 1 kilomole of fuel. If we want to change this to air to fuel ratio by mass, we multiply by the molecular weight of air divided by the molecular weight of fuel. This will give us this value here. Okay, this is another example here. All right. So now let us go back here and say theoretical and actual combustion process. What is the difference between this? And the difference, as I mentioned here, that in the actual practice, then we may have fuels here. In the actual practice, of course, we add more air. So in the theoretical, we have fuel, we have air, and we get CO2, H2O, and without any excess oxygen. If this is actual, then we have here excess oxygen. Why I add more air? Because I want to make sure that I burn all the fuel. So I have to get more air for every particle of the fuel to burn. To make this, I have to have extra air. So this is in life here, we give more air. Of course, also in life, sometimes we find unburned fuel here. So let us go through this here. So this is complete combustion. Complete combustion means that all carbon in the fuel burns to CO2, all hydrogen burns to H2O, all sulfur, if any, burns to CO2. We say this is complete combustion. Means that we have no chance for any fuel to appear in the process. When I say incomplete combustion, means that if the combustion products contains any unburned fuel like carbon, hydrogen, carbon monoxide, or H. This is when you go and test your car, you find that it fails, for example, because it has a lot of carbon monoxide here in the product, then you have to go and adjust the carburetor or the injection, the mixing process to get that. Sometimes you go behind a truck or a car and find that there's a black carbon coming out, and means that this is incomplete combustion. So you see carbon monoxide coming, this is incomplete combustion. The reason for incomplete combustion can be to some reason. Maybe insufficient oxygen, there's no main oxygen here, or you have the right amount of oxygen, but you do not have good mixing of the fuel and air. So if you have not good mixing, if you have insufficient oxygen, it's likely to have here incomplete combustion. So what I want to say here, what's the difference between complete combustion and incomplete combustion? Complete combustion means you have no fuel here. Incomplete combustion, you have some unburned hydrocarbons in the products. Okay. Now we call it with theoretical air. We mentioned that theoretical air will be mean that you have complete combustion with the minimum amount of air. In the engineering, combustion engineering, we call theoretical air, we call it stoichiometric air. So we will find this expression instead of theoretical sometime. So when we say stoichiometric, it is exactly the same as we say theoretical. And this is here stoichiometric or theoretical combustion. This is an example here. CH4 plus 2O2 multiplied by plus 3.76. This will give us CO2, hydrogen will give us H2O, and then we have no extra oxygen here, we have no extra fuel here. So there's no unburned fuel, there's no free oxygen in the product. This is what we call here theoretical or stoichiometric. Okay. Then we say here excess air. So excess air means that the amount of air in excess of stoichiometric amount. So now we have excess air. So I can say 50% excess air, which is the same as 150% of the theoretical air. So this is how do we write it here? So we're writing this equation again here. It is the same equation. All what we added here is this, instead of 1 here, it was 1, we make it 1.5. 1.5 represents that I have 150 times the theoretical air. Or we say here that we have 50% excess air. Then once we write this, then we should say here that we have excess oxygen here, and then we complete the reaction equation. This is an example of deficiency of air. Suppose you have incomplete combustion. If you have incomplete combustion, you will find here that you have some carbon monoxide here in the product. So you will find that carbon, part of it will burn to CO2, and part of it will burn to carbon monoxide. Therefore, carbon monoxide can still burn, and therefore we say here that this is incomplete combustion. So now we have stoichiometric or theoretical, we have excess air, and we have deficiency of air. These are the three cases that we find. This is the two cases that we find in practice, that you have excess air or you have deficiency of air. But this is the theoretical air. Of course, this is not practical, because this will produce a lot of, because due to unmixing, definitely we'll find that this is deficient air. Okay. So we define the air to fuel ratio on a mass basis, that it is the percent of excessive theoretical air. This is the actual air to fuel ratio over the air to fuel ratio. This will call it here percent theoretical air. Percent excess air will be the actual air minus the theoretical air over the theoretical air. So we call it also excess air factor, which is the air to fuel ratio actual over air to fuel ratio theoretical. Sometimes we call it excess air factor. Also, in many applications, you will find the definition fuel to air ratio. This should not bother you. It is just the fuel over the air. Here we have air to fuel ratio. This is the mass of air over the mass of fuel. Here, fuel to air, this is the mass of air over mass of fuel. And sometimes we will not use this much in your course here, but later on in other courses you'll find equivalence ratio. Equivalence ratio is the fuel to air actual over the fuel to air theoretical. Let me go to this figure here. Do you see this figure, Shabab? Is it clear?
Yes, doctor. Yes.
Okay. Okay. Let us read this figure. This line here is the air to fuel ratio. So this is the air to fuel ratio, and here we have, this is what we call the air to fuel ratio theoretical. So this is when we calculate the air to fuel ratio theoretical, it will come to around 15. Last time we calculated that, it comes to around 15, 17, depending on the fuel. And this is here when we go we have more air than the air to fuel ratio theoretical. When we increase the air, we call this is lean mixture. When we have less air or more fuel, we call it rich. Rich because it has more fuel. Because whoever has the fuel, it is more rich. Because this is lean here, it is more air. The air is free, so this is lean mixture. We call this is rich mixture. What is 244 here? 244, these are we call the flammability limits. Means that within this range, when you mix the air and fuel, you burn them, it will burn. But if you go more than 44, it may not burn. This is why sometimes you are in the gas station and they tell you, please switch your car, switch your mobile, you have a spark and you may burn the fuel, the mixture, and you do not bother about that and nothing happens. Nothing happens because we are beyond this region here. Beyond this region, you will have air and fuel in the gas station. You can smell gasoline, but nothing burns. Why? Because we are outside this region. But if you are unlucky and you are inside this region here, then you will have a disaster in the gas station. Okay, so this is here what we call flammability limits. If the air to fuel ratio is less than 2, it will not burn. If the air to fuel ratio is more than 44, it will not burn. Then within this region here, then we have what we call the theoretical air. This is here the air to fuel ratio theoretical, which means that you have no extra fuel, no extra air, just the theoretical air, complete combustion with no exhaust. Okay, where do we work in our life? We work in the lean mixture or in the rich mixture in your car. Does it work in the lean mixture or in the rich mixture?
Lean mixture.
In lean mixture. Why? Because this is recommended. Why? Because it's economy. So when you go in this direction, it's likely that you burn all the fuel. When you burn in this direction, it is likely that you will have extra fuel here. And of course, because the air is free, I can get more air, and then I have extra air here. But if I have extra fuel, then I'm losing the amount. When you go to the station, you pay only for fuel. You do not pay for air, at least for now. But therefore, if you work in the rich mixture, means that you are going to have fuel in the product. So this is the recommended or the economy. So all of our cars runs in this region here. And this will be around 20% excess air. So this will be around 20 or 30 the air to fuel ratio. Okay, how about this one here? Who works in this? Okay, this is here, you know, Ferrari and for races, car races, they do not care about economy, right? If you are having a race for car race, then in this case you will worry about power. Also you need is to go faster, and therefore you do not worry about extra fuel used here, but you need more power. So if you need more power, you will work in this region here. So this will be less than the air to fuel ratio. So this is the economy region, which all of our cars work on, and this is the power region for car racing. Then they use this region because they have more power. They do not care about the economy in this part. All right, Shabab, do you understand fully this figure? If you have any questions.
دكتور ليش
Yes, please.
إذا قلنا الهواء يزيد البوق شو السبب؟
ليش وات يا فيصل؟
إذا قلنا نسبة الإير تو فيول ريشيو يزيد البوق شو السبب؟
Okay, I answer that. Okay, you have a size in the engine, right? In the engine, you say it is 1.4 liter, for example. And either you fill this with fuel, make sure that you are having the right amount of fuel, or you have the extra air. So in this case, you are utilizing the engine here, the volume of the cylinder. So now we have more fuel, and therefore you will get more power. The power is related to the mass of fuel multiplied by the amount of the size of the that you can put in the size of the engine. So when you have, if I compare Faisal with Muhannad, for example, then Faisal has his car in this region, means that he has more fuel in his engine, and Muhannad has more air in his engine, and therefore in this case you get more power than what he has here. Okay, so it is how do you utilize the volume of the cylinder? Because when you put air, if you put 100% air here or just small amount of air, only this amount of fuel will burn with air. But if you put this amount here, then you make sure that you have more fuel is burned, and therefore you get more high temperature, and then you get more power. Okay, Faisal?
Clear, thank you.
Okay. So now let me go now to some more examples. I want to make sure that the first part, A and B, are 100% complete. No mistakes by any of students. So now let us take here an example. So write the reaction equation for octane and with 120% theoretical air. 100% theoretical air means 20% excess air. So now how do I write this equation? This is the way I do it. I write here C8H18. Then I go here and write CO2 and balance the CO2, so this will be 8 CO2. Then I go here and write H2O. Balance H2O, so this is 18, this is 2 here, so this will be 9. So the first step I write that, then I come here, write 8 CO2, then I write here 9 H2O. Alas, this is the reaction for the fuel. Then we come to balance the oxygen. Okay, balance the oxygen here for theoretical air. So I have here 9. So this will be 4.5 because this is, so 4.5 moles. And this is here 4.5, and this is 8 here. So 4.5 plus 8 will give me 12.5. So this is I balance the oxygen here. 8 plus 9 over 2, so this will give me 12.5. Then I write here, so this is the theoretical air. So now I finish the theoretical air. C8 will give me 8 CO2, H18 will give me 9 H2O, then the oxygen 4.5 plus 8 will give me 12.5. So this will be the theoretical air. I do not need the theoretical air, it's telling me add 20%. So I write here 1.2. This will not change, this will not change. 1.2 will give me here, I need only 1 to give me those, but then I have 0.2 extra, so I add 0.2 multiplied by 12.5, this will give me the amount of oxygen. Then for nitrogen, I multiply this by 3.76, I get that. Shabab, 100% correct, huh?
Inshallah.
Inshallah, I don't want any, because this will have consequences on the other parts. And this is easy for you. Just be patient a little bit, do some exercises, and you will make it, you will be expert in that. So this will be the answer for this part. Some other books do that. They write it here, C8H18 plus 1.2 multiplied by the A theoretical, and write the equation like that. And then try to rebalance the oxygen here and get A theoretical as we have calculated it. But this is normally the way I can calculate it. It's easy here to write 8. This is 9. Then 4.5 plus 8, 12.5. This is, you get it here. Or you wanted to do this way, it's fine here. So this is the blind way, is to put A theoretical and then write the equation, you get the value from that. Okay. Another example here is just for deficient air. So it says consider combustion of C8H18 with 120% theoretical air, where 80% of carbon goes to CO2. So what I do in this case, he says 0.8 will build CO2. So I have, if it is complete combustion, this will give me 8. But now it is not, so I'll put 0.8 here. Then the remaining here for carbon monoxide. So it is 0.2 multiplied by 8 will give me carbon monoxide. So this is the amount of carbon monoxide. So theoretically, it is 8 here. Theoretically, this is 8. Now 80%, so I'll have 80% of that, of the 8, and 0.2, 20% of this will go to CO. Hydrogen will stay the same, so this will write the equation as this here. To balance the carbon, then we write the equation here. We have this is on the left-hand side, and this is on the right-hand side. Then we can calculate the amount of oxygen coming out here. So this is also for deficient air, or air is less than the fuel, and therefore you will get some unburned fuel here. So this is what we call incomplete combustion. And this is what causes the tail of black color at the end of some trucks in front of you when you run in the airways, so in the highways. So now let us go once more here, once and final here, C3H8. Okay. I want one by one to give me here what is the balance for that. Just read it here, it is given here. So 3, I put here 3. Then 8, I put 4 here. Then oxygen will be 2 plus 3 will give me 5 here. So this is here is writing the theoretical equation, theoretical combustion reaction equation. The air to fuel ratio for that, let us calculate it together here. I want to calculate the air to fuel ratio. So I'm calculating the mass of air. What is the mass of air? This is the air here. Can we calculate the mass of that? I have 5 O2. O2, the weight is 5 by multiplied by 32. So this is the mass of oxygen. Then plus the mass of nitrogen. It's 5 multiplied by 3.76 multiplied by 20. So this will give me the mass of oxygen plus the mass of nitrogen. So this is the mass of air. What is the mass of fuel? It is 3 by 12 plus 8. And this will give me the value here, air to fuel ratio theoretical. Is it clear, Shabab? So
Yes.
So two things I need for.
Right?
What is that?
The molar mass of hydrogen is 8 multiplied by 1, right?
Yes, right. Yeah. Wait a minute. Okay. How many moles of air here? 5 oxygen plus 5 multiplied by 376 nitrogen. So it's 5 multiplied by 4.76. That's the only thing you missing, Faisal. 5 multiplied by 4.76. This is a mole divided by 1 here. So let me repeat this again, it's important. What's the number of moles here? 5 plus 5 multiplied by this. Or it is 5 multiplied by 4.76. So this is the number of moles of air. Divided by this will give me the air to fuel ratio theoretical on a mole base. On a mass basis, because this is most of the time will ask you for the mass base. Mass base is here, so it's 5 by 32 plus 5 by 3.76. Okay. Let us do this in another way. Now, as Faisal was just asking now, what is the number of moles of air? It is 5 multiplied by 4.76, which is 1 plus this. So 5 multiplied by 4, this is the number of moles of air. Then I multiplied by the molecular weight of air. Divided by 44, this will give me the same value. So this is two methods here. Either you calculate it from add the mass of oxygen plus the mass of nitrogen, or see how many moles of air and multiply by the molecular weight of air. Then divide by the molecular weight of fuel, which is given here. So this will give you the air to fuel ratio. No mistakes, please. Please, no mistakes. This is here for theoretical air. How to write the equation and how to get the air to fuel ratio theoretical. Either this way or this one. No mistakes, please. No mistakes. You do this. Be an expert by solving just some examples. Okay. When we say 120% theoretical air, then we have this is the same meaning as you say 20% excess air. 120% theoretical air is exactly the same as you express it in 20% excess air. So I write this for the same fuel here. So I copy this here. This is the blue color here. This is the same. But then I add the red color here. Now I add 1.2. It was 1 here. This was 1. Now I make it 1.2 because he's asking for that. Then 1.2, this will stay the same. No change in that. 1.2 here. Then it will give me here. I have 1 to satisfy this, but the extra here is 0.2 multiplied by 5. So I add this. This is a new term. It will appear here. This appears because there's an excess air. So this will be 0.2 multiplied by 0.5. This is one key point here. Some students make a mistake here and write this 1.2. This is not correct because this is 1.2. I used 1 here and the remaining is 0.2 here. So this is the only mistake that some students do. Some students write this 1.2. This is not correct because the extra here is 0.2. So I have to write 0.2 here. Some other students forget the 5 here. Okay, you should write 5 here because this is 0.2 multiplied by 5. So this is the only mistake that some students do. For the nitrogen, it remains you multiply this, all of that by 3.76 to give you that. Then how to calculate the head-to-fuel ratio? It is the same as you have done here, just add 1.2 and multiply it here 1.2. This will give me this value. So this slide here has to be correct, 100% correctly written. So please review this again. Okay. Let me give you an assignment now. I'm not asking you to submit it, but let us do it now. If you do it correctly now, I will not ask you to submit it before next class. This is a general question here. I want every one of you, only one of you answers one. Okay, so I need one by one. So now what should I write? This is CnHm. So this is a general equation. Okay. What is the value here?
N multiplied by
N is so the value here should be N. Okay, another student, don't answer again. What's the value here?
N over 2.
M over 2, very good. Okay, what is the value here? A third one, please. We have now N here. We have M over 2 here. What is the value should be here? How many moles of oxygen now? I have N here, M over 2 here. So what's the value here?
N plus M over 2.
Plus M over 2. N moles of O2. But here I have M over 2. Atoms. So how many moles?
N plus M.
Now we have N. All of you agree that we have N here plus. Plus what? I have M over 2.
N
how many
plus
moles?
M over 4.
Very good. So N here is number of moles of O2. Here I have M over 2. M over O, 2 atoms of oxygen. So this has to be N plus M over 4. All right. What is the value here? We repeat N plus M over 4, we'll multiply by 3.76. Okay, so every one of you, please complete that. And I ask as the one who answered N plus M over 4, who is that? Who give me the answer in? Anas, okay, Anas. Can I ask you a favor, please? Complete this equation and send it to all on WhatsApp. So write here N, M plus M over 2, N plus M over 4, and here N plus M over 4. And send it to all students. But before that, or not today, tomorrow. So every one of you try to do that, and you will have the answer. Anas will put it for us on WhatsApp tomorrow morning, inshallah. Okay, Anas, do you agree?
Inshallah.
Inshallah, jazakallah khair. Thank you very much. Okay, so there is no need to submit that, but you have to do it before for next class. You have to make sure that you are. If you do that, khalas, any fuel will be N is a certain value, M is a certain value. All right. Okay, now the one important question here. When we wrote this equation here, one of those here, what is the base here? This is 1 kilomole here. Okay, so this here is the performance of fuel in the gas station. We did not put it in the car yet. So the car influence does not have anything here. Okay, so now this is per kilomole of fuel. This applies for when every one of us goes to the gas station, then he will find that this applies that. This is a characteristic of the fuel there. Has nothing to do with our cars. Okay, so this is here is the performance of the fuel per kilomole. So if I go and buy propane, which is C3H8, then I find that the air-to-fuel ratio behave like that. If I add this, it will behave like that. So this is a characteristic of the fuel at the gas station. Now we take this fuel, you know, to measure the air-to-fuel ratio in your car or not. Do you have any indicator to tell you how much air you used? Ya Shabab. Do we have any measure in your car for the fuel? شباب, where are you?
For fuel
ما
or
أعرف يا دكتور.
Yeah, can you read the measure for the fuel in your car? You know how much
Yes.
fuel you have in your car. Okay. How
Yes,
about
yes.
the air? How about, do you have any measure for the air?
I don't think so.
No.
Yeah, we do not have any. In all industry, we do not measure the air. All right, we do not have any measure for the air. Okay, so in boilers and gas turbines, and we just have the air comes and we adjust it here. But how do we know it is correct or wrong? This is the issue that I want to discuss here. So remember here that this is based on 1 kilomole fuel, and this is the characteristic of the, we write this equation and we get from this equation the amount of air that we need for theoretical air. But what happens in practice? Okay, how do we measure the air? This is, look at this slide here. When you go to the inspection of your car, did anyone go to inspection of his car? Volunteer يا شباب, did anyone go there? No one, huh?
وش inspection يا دكتور؟
Inspection of your car to every year or every 3 years, you have to have a sticker in your car that this passed inspection.
Yes.
I have it on my car. It says that it is finishing on May, for example, certain year. Every car has like that, or otherwise you will take a violation.
Okay.
Did you get that in your car?
Yes.
You have a sticker there. Okay, so when you go to the inspection, it is in the way to Riyadh, somewhere there, and you, when you go to Riyadh, then you will find this. It's Buhadriya, I believe, Buhadriya Road. It is on Buhadriya. When you go to the airport, you'll find something like that that tells you car inspection or something. This is what they do. They measure the air to fuel ratio. And this is, I put this here as when you go to the, sometimes you take a child or something, or young boy, and go to the clinic. And they do not know, you do not know what he ate. He has something in his stomach and you do not know what he ate. What he ate here is what is like the car in the air in the car. The car takes air here. So when you have a child, he eats something, you don't know what happens, but he has something in his stomach. Then you go to the clinic and they make some analysis and they see, because he cannot tell. So they tell you here what did he eat. For the analysis. This is what we do for the car, as a matter of fact. Then we do not measure the air, as I mentioned. In any combustion process, we do not measure the air. Then what they do, if one of you just remembers what happens in this car, then they take a sample here, and this sample they remove the water vapor, and therefore the products here will be CO2, oxygen, nitrogen, and carbon monoxide. They have a gas analyzer here. And with this gas analyzer, they can tell how much air is that, what is the air to fuel ratio. So this is the way in all of our industry how to measure the air. We do not measure the air coming here, but we make the analysis of the products, and this analysis will tell us how much air we have here. And this will be the next step that we call here, this is here dry product analysis here. So this is exactly what happens here. I want to know what the air to fuel ratio actual now, not theoretical. So this is similar to all of us take one sandwich, the same sandwich, and some of us will get some problem with their stomach, some will be okay, and maybe one will die from that. So this is not the responsibility of the sandwich, but it is something happens in our stomach here. So this is, therefore, we need to analyze for each car now. So for the car here, when we use this equation for the theoretical air, then this is the fuel in the gas station. But once you put it in each car, the performance will be different here, because some of them will give incomplete combustion, the spark plug is not working, there is a leakage in the cylinder. So we need to test what is the actual air to fuel ratio now. This is the theoretical air to fuel ratio, but we need to calculate what is the actual air to fuel. As I mentioned, we do not measure it here. We have no measure for that. But what we do here is to take a sample of the gases and then make a gas analysis here. But we remove the water vapor. Why we remove the water vapor? Because we know that it is a feature of the water that will have corrosion to wrappers and so on. So this is here, we remove the water vapor and then we pass it to a gas analyzer. This gas analyzer will give us the percentage of this. And from this, I want to come back and make the air fluoridation. So this will be your business now. You went to the gas station, to the inspection, and they tell you how much CO2, how much oxygen, how much carbon monoxide, and how much. They will give you this analysis. So you write here. So for example, this is for CO2, for 16 carbon monoxide, 80 nitrogen. This is given to you. And what I need from you here is to write this equation and calculate the air fluoridation. You see the problem now, Shabab. Okay. Now, as I mentioned, we do not measure the air fluoridation. But how to measure it? This is the actual now. We take a sample, and this sample we remove water vapor because it is dangerous. It is a corrosive material for wrapper and so on. And then we have this sample here. So this is a gas, the sample. The sample, we make it dry by removing the water vapor. So this is called dry gas sample. We put it in an equipment here, and this equipment will give us here the percentage of each one of these. Your responsibility. So this will be the question. I'll give you the analysis here because this we can read in the inspection site. And then from this here, I want you to come up with the air fluoridation. Okay, this is the question, Shabab. You read that. So the question is that this is given to you. What is the air fluoridation? Is the question clear? Just a question.
Yes.
Yes.
Okay. So now, okay. So now what do I know? What do I know here? Okay. Now we have to write here that the fuel is CH4. This will be given. And we know that I write this bracket as well. So to write this equation, I write CH4 here, and then I write O2 plus 3.76. But I do not know how much amount here. In the stereochemical combustion, this was 1, so this is based on 1. But what is the base here? The base here is based on 100 kilomole of dry product. So this is 100 here, 4 plus 16 plus 10. So I write here the equation, but I put A here. And then because we removed the H2O here, I have to put it back here. So this, you are given that. Then to complete the equation, you have to write this here at A. You have to write this part here and then balance to get the oxygen. So this is the port. Let me tell you what the students make mistake here. In the next exam, I will have 2 students writing this is 1, forgetting A here. This is a problem. This is not correct. Okay. Some students will forget that. I'm telling you about the tricks now. I'm telling you that I will have 2 students in the next exam forgetting that. Do you challenge me? I will have 2 students forgetting A here. If you write this A and write this C, خلاص, this solve it now. So you can balance carbon, so A will be equal to 4 now. You can balance. No, A will be equal to 4 plus 16. This is a balance for carbon in this case. And then you balance for hydrogen, and you balance for hydrogen to get C. So you balance carbon, get A. You balance hydrogen to get C. Then you balance oxygen to get B. Okay, Shabab, I leave you at this stage, but please read this slide again. Think about it. Think about the practice. This is actual case we have when you go to the inspection. Okay, so this is the actual case of how to measure this, and this is what we do in the clinic. When you go to the clinic and you don't know what did you eat, or let me say one child or a young man or so, he doesn't know, he cannot tell, then the physician will take a sample and then go to the analysis and then come with this analysis, oh, you have eaten something and so on. This is what we do in the car. We do not know what the amount of air here, and therefore we measure that. We measure that. And then from this equation, this is given now to us. We complete get A, we balance get A, we balance get C, and balance get B, and then we calculate the air differential. So please read this here and read this one. I will repeat this next time. I'll repeat this next time again. I'll start from here. Okay, thank you much. Let me just take attendance before you leave. And then if you have any question, we can talk about. Let me just go back here and take attendance before I forget. Okay, so خلاص I downloaded the attendance. If you want to leave, that's fine. If you have a question, I'm staying with you here.
تقدر ترفع السلايدات يا دكتور عبد
السلايدز بسرعة. I will repeat it this next time, Faisal, okay?
اقول لا
normal-
ابلود ذا سلايد
You are right. خلاص I will do that inshallah. I will do this right away after the class. I will upload on an updated version now, which is the one I have now.
ثانك يو.
You are welcome. Thank you, Faisal, for reminding me. جزاك الله خير. Any other comments, شباب؟